So at the end of lecture 1, we wound up with the wave equation. And this was a fairly physics-based lecture where we got insight into the important physics, but I also wanted to approach that, that result with a bit of practical insight. And a number of these lectures I will be calling practical acoustics. They'll be quite short and hopefully quite useful in understanding some of the basics. And so here I've started off with our wave equation, and we have the result, which is pressure as a function of space and time. And of course, in the real life, the real world, practically, we just measure it in time. So you put out a hydrophone, it's fixed in space, and it samples, at a very high rate, thousands, tens of thousands, hundreds of thousands of times a second, and you get a time series from that. Now, even more practically, you're not really actually measuring pressure, you're actually just measuring voltage or a digital number from your hydrophone. So your hydrophone is plugged into something that converts the analog signal, right, the vibrations in voltage, to a digital number. The digital number gets written to a wave file or some sort of file. And practically, when you look at some papers, we like to report results in acoustics using decibels. Why? Well, partly because the range of measure is huge. It's like 10,000. The quietest sound we can hear is about 10,000 times quieter than the loudest sound we can hear. And of course, in the physical world, we go, beyond that even. So it's a huge range, and these decibels are all about logs of ratios of power. And the important thing here is that these are ratios and powers. So ratios of powers. And really at this point, we have two choices. One, we can look at relative ratios. So that's where the reference pressure is going to be something like a maximum pressure, or maybe a noise level, or it could be, yesterday's measurement compared to today's measurement, or maybe a measurement from 1 meter compared to a measurement from, 1 kilometer. Or we can go with a referenced ratio, and that's where the reference pressure is an absolute measure of pressure, which means that our measurements in the reference pressure can be compared to any other measurement in that reference pressure, because it's actually related to the pascals. In water, that reference pressure is 1 micropascal. That's 1 times 10 to the negative 6 pascals. In air, I think the old standard, or maybe the current standard, is 20 micropascals. Lots of different authors have chosen lots of different reference pressures over the years, but that one with water, seawater, is sticking around. It's here to stay. So we have two choices, relative or a reference. And here I'm going to talk a little bit about the idea of a relative ratio. And the nice thing about being able to look at these relative ratios of powers is you can start with any form of the signal. So you can have a digital signal, you can have a voltage, you can have a pressure. You stick them into your equation where you have the thing you actually measured and the thing you want to use as a reference. You take 20 log 10 of that, or 10 times log of the square of that, and that gives you a dB measure, right? So it's a very straightforward, simple way to understand, how much quieter, how much louder your measurement is. Now, these two equivalent forms are, of course, because of this log rule. If you feel a little bit rusty on that, absolutely just pause this lecture, go to Wikipedia, look at the properties of logarithms. Wow, what a wonderful tool. Read the history part. Why not? Why the squared? Why is this defined this way? So why is the actual definition of dB 20 log 10 the value over the other value? That's because it's a ratio of powers. And in most cases, for instance, voltage squared is proportional to intensity, and pressure squared is proportional to intensity. So truly we're looking at a ratio of powers when we square it. And that's why there's a 20 log 10 of the absolute value, or 10 log 10 of the square. So for an example here, I have a little example where, on the y-axis, we have either bits or volts or pressure. We have it recorded, and then all of a sudden there's a loud blip. And one thing you might do is, okay, let's figure out how many dB is our blip above the background noise, or in other words, what's the signal to noise ratio? And so you can square that signal. Now you're going to have bits squared, volts squared, pascals squared. Everything's going to be greater than 0 now. Here's your blip. And you can, easily just read off, okay, where's my noise level? Read off where the peak of this is, and then just take 10 log 10 of the two values, and that gives you your SNR, or signal to noise ratio, in dB. Okay, very practical, and like I said, X here could be bits, it could be volts, it could be pascals. It doesn't have to be, very carefully calibrated, and so you can get away with, not having a really skookum system for that. For the reference ratio, right, now we want to actually reference our dBs to physical reality. And so typically, let's say you have your digital signal here, Xi-n, right? You need some way to convert it from from bits to volts. And so to calculate this conversion coefficient, for example, say you have a 24-bit wave file. Well, 23 of those bits are used to count numbers. 1 bit is used to mark a sign. And I'm going to just say you have a plus or minus 5 volt analog to digital converter here. So your biggest number is going to be 2 to the 23. Your biggest voltage is going to be 5 volts. Your smallest is going to be minus 2 to the 23, and your smallest voltage is going to be minus 5 volts. You can use either of those ratios to compute this Q coefficient. To get from volts to pascals here, now you're going to need to know how to convert between those two. So basically, this is a physical measure of the properties of your transducer. So you have some little ceramic that's vibrating. How much voltage does it generate when it's vibrated by a sound of a certain amplitude? This is usually supplied by the manufacturer, or you've sent it away to get calibrated, or maybe you've done the calibration yourself, but it's typically a hard thing. But the nice thing is that your pressure is just a product of these three things, and that should give you pressure in pascals, the actual the actual thing we had written down in our wave equation. So here I've given another little example where we have pascals on the y-axis now. Here's your time trace. It's quite zoomed in compared to the last example, or maybe it's a very low frequency. And just the idea that you might take a single point and you want to know what's the pressure of that point in dBs reference to 1 micropascal. And it's quite simple. You would just take that pressure reading, you put in your formula, square it and divide it by the reference pressure, which is 1 micropascal, and of course it has to be squared as well, and that would give you this value in dBs re 1 micropascal. You could also do 20 log of the absolute value, of course. And typically, reading one single pressure sample isn't really done, but you might say calculate the RMS, right? The root mean squared of some 1 second segment or 10-second segment, or who knows. And then you can take that PRMS, right, which is just the root of the mean of the squared values of that time series. And then you could calculate the dB re 1 micropascal by, again, just putting it into either one of these. And you would indicate that it's the root mean squared by saying the dB RMS re 1 micropascal. Now, the complication to all of this really lies with this factor m. So m is typically, and by typically I mean always, it's a function of frequency. And so really what we need to do to do this properly is to take our take our pressure time series into the frequency domain. And I'm going to leave that for our next little bit of lecture on practical acoustics. Thanks.